Hello! Today's lesson is about a thing in physics called the electromagnetic spectrum. And that's a very, very fancy word to encompass all things that essentially are a lot like light, but that we can't necessarily see them. One of my favourite quotes is by a guy called Neil deGrasse Tyson on this topic. And he was in a lecture and he said, when you understand the electromagnetic spectrum, you understand just how blind we are as a species. We are very, very, very interested in what we call the visible spectrum because it's what we can see. It's what our eyes pick up. It's how we find our way around, and we can tell so much richness from colours and textures and things we can see. But we are looking at this tiny, tiny little sliver of what is out there. And it turns out that once you go outside of that, you have a load of things, a load of different regions of this spectrum that we describe very much and behave very much in many ways similar to light, but will have slightly different uses, different properties, and occasionally different dangers. And so what we're going to do today is I'm going to take you through those different regions, how they were discovered, and kind of some of their uses and a bit of their history. I hope you enjoy it. Now, the story of the EM spectrum, the electromagnetic spectrum, should start really with the bit that you know about, which is visible light. Okay, and you might be aware visible light can come in lots of different colours, so you can make it in all these different colours. But if we deal with white light, the first time the spectrum was determined was by Isaac Newton back in the 1660s, when he did an experiment where he took sunlight that was falling through a window and he let it fall onto a prism. And by passing it through a prism, he was able to generate the rainbow. And there we go. This idea, not too bothered about that, this suddenly sort of changed a lot of people's understanding about how light behaved. Rather than there being lots of colours and white as its own unique colour, we then started to see that white itself was just made up of all the colours. And this is the first thing of what we would call a spectrum. A spectrum is just a range of things that all behave in very similar ways, all have very similar properties, but just something about them makes it slightly different. So the spectrum of visible light goes red, orange, yellow, green, blue, indigo, violet. Had a brief sort of memory lapse there. So the Roy G. Biv of the rainbow. And this is where we are going to start sort of as our anchor point of these things. But it turns out that there is, to everyone's surprise, there are things that sit outside of the visible spectrum. Areas of things that are like light, but we just can't see. So we start with the visible spectrum as discovered and sort of highlighted by Isaac Newton back in the 1660s. That's the bit everyone can see, the Roy G. Biv, the visible spectrum. And so the electromagnetic spectrum is just this extended off into places that our eye cannot see. And so the first thing that was, the first addition to this happened in 1800 with the work of William Herschel. Now, if you are familiar with some of science history, you might recognise the term Herschel. You may have seen if you ever go to the observatory down in London. William Herschel is one of the preeminent astronomers of his day. In fact, in 1781, he discovers Uranus. He's the first person to observe, by having built a giant telescope, a sort of like a planet that is not visible to the naked eye. So you can see always the ones up to Saturn. Uranus is the next one, and although you can very occasionally see it with the naked eye, it's not visible all the time. And so you need a telescope to be able to track it properly. And he discovered Uranus. But in 1800, he published a series of studies that he did in the Royal Society. And what he did was he knew that if you took if you stood in the sun wearing, if you stand in the sunshine, you get hotter. So something from the sun, as these rays of sunlight come down, you get an increase in temperature. And what he wanted to uncover is whether that was due equally to all of the different parts of the visible spectrum. Is it due to all of it? Does the red light and the orange light and the green light and the blue light, do they all give you the same sort of amount of energy that leads to you getting hot when you're in the sun? And so he did this with a very ingenious experiment. He took sunlight, passes it through a prism to split it up, and you end up with the blue end and the red end. So there's your red and there's your blue, going to the indigo and violet and so on. So, and what he did was he said, okay, I'm going to have a series of thermometers. And so this light is going to shine on a thermometer. And he had the thermometer in the patch of blue light or violet light and measured how long it took for the temperature to rise. And he noticed as he brought it through the visible spectrum, you ended up with things getting hotter, quicker. So red light was able to increase the temperature of things more rapidly than blue light. But then what he did was somewhat ingenious. He then stuck the thermometer just here, just beyond the colour of red that you can see. And it was here in this region that he found that the temperature increased the fastest. And that discovery told him that there must be this kind of weird, mysterious radiation, this weird, mysterious stuff just beyond where you could see that was responsible for the feeling of warmth that you get when you hold your hand out into the sunshine, that it was mostly responsible in this region here. And because it was nearly red light, it became known as infrared. Infrared radiation. And so it ended up going here. And that was the first inkling that there was... Now, infrared radiation, the modern usage of it, it will be anywhere. Normally you want to heat things up. So ovens and toasters, they use infrared radiation because they basically make something hot and they get very hot and they start emitting this kind of radiation. But the other place you find infrared radiation being used is inside a remote control. And that's because when you want to turn your television on, you'll hit a button and it will send a message to the TV. And inside here is a little infrared LED. Now obviously it's infrared because if you take your remote and point it at your own face and like hit a button, you won't see anything because your eyes can't detect it. But on phone cameras, and particularly the ones that are facing towards the front-facing phone camera, not the very nice one with all the lenses that's pointing away, but the slightly lower quality one that points towards you, they actually detect infrared radiation because they don't have the filters necessary to remove it, and so they try and do with it what they can. So if I point this at the camera and I push a button, you'll see inside a little thing light up. It's an LED. And it's pulsing, it's sending little messages with infrared radiation, and it's confusing my television, which is just over here. And it's utterly invisible to the naked eye. So have a bit of a test. Get yourself a remote control. Get your iPhone camera or whatever it is you're using. Have it the one facing towards you, and see if you push it towards it, will it suddenly pick up this infrared radiation that is there. The ones that are facing outwards tend not to detect it. They tend to be a bit better, and that's because actually infrared radiation is around you, and if your camera is doing stuff with it, then actually what it will, and particularly it's turning it this weird violet-y sort of colour on mine, then what that would do would be to ruin the photo. It will add extra colours in that it's not supposed to have. And so, yeah, so this is one of the other places. So toasters, ovens, remote controls, modern uses of infrared radiation. The next discovery was very quickly afterwards. In fact, it was in 1801 by a scientist called Johann Ritter. And he does an experiment that's actually very similar, but kind of the other way. One of the other things that light can do is it can be used to take photographs. And what happens when you take a photograph is that you have a camera shutter and you've got a lens system and so on. But you have a film, okay? And that is made or immersed in silver chloride, which I probably haven't got the atomic symbol, the actual formal symbol is. But there's a silver chloride soaked paper. That's what photographic film in the early days was. And what would happen is you would open up the camera shutter opens, a load of light goes in, and as a result of the chemical reaction, the film itself darkens. So I'm going to have to use a sort of so it goes from light and clear to dark. And you might be aware this is when you look at photograph films, or there's like settings in this to talk about the negative. And that's where basically everything's reversed. So to make pictures out of this, you tend to then have to work backwards from the negative. So it's almost the shadow, the dark bit is where light has fallen, and the light bit is where shadows haven't fallen. So it's where light hasn't fallen. So this silver chloride paper is darkened by visible light falling on it. And he did a very similar experiment. So what he did was to take a very simple camera setup, and in the same way by using a prism setup, was to make sure that only one colour at a time would go through the screen. So starting with, say, red, and then turning in some, yellow light, and then all the way up to blue light. So by doing the same thing, but instead of putting a thermometer, that's just where he angled his camera film. And he was timing how long does it take for this shadow, this darkening of the film to occur, like how long to darken the film. And he discovered almost actually the opposite of Herschel. He found that when you were putting these different velocity of light in, he found that for taking pictures, you had the infrared rays that had been discovered. They were the slowest to darken, up to violet, which would be the fastest. So, and then you have the red, and you go Roy G. Biv. So as you went through, the chemical reaction that was occurring was happening quicker when you went to the violet end. And so like Herschel, he thought, maybe I should have a quick look at what's going on beyond the ultraviolet. So is there anything beyond the violet spectrum? So in a weird world where you're putting some invisible rays, you can't see anything going into the camera. There's no rays of light that we can visibly see going into the cameras, but we did still find that this was darkened much, much more quickly. So there was an invisible ray of light going in that you couldn't see and was causing the film to darken. And those became known as ultraviolet. Beyond the violet, higher than violet. So infrared, lower than red, ultraviolet, higher than violet. And that is the second region of the electromagnetic spectrum that was added, and for a very long time. The next expansion of the electromagnetic spectrum wouldn't come until towards the end of the century. So 1886, I think it might be a year, it might be 1887, with not Wilhelm, with Heinrich Hertz. He of the unit of frequency. And Hertz was building on the work of a fellow called James Clerk Maxwell, who derived a load of laws for how waves of light we would move around space. And so he was testing to see whether he could find some other examples of them, because there was starting to be a prediction that there should be stuff here and there should be stuff here. So Hertz builds a rather ingenious contraption. He builds the first radio transmitter and detector. And in a very, very, very simple way, this is a radio transmitter. It's a circuit, but it's got a very, very, very small gap in it. And you might know from seeing from occasionally some of the stuff you might do around electrical circuits, you might notice that if you've got a small gap in something and the gap's small enough, what you can sometimes get is a little spark. So a little lightning bolt that jumps across the gap, which is essentially what lightning is. It's just a much bigger gap. And so he built this thing. It's more complex than this to look at, but this will do. And he built this. And so you close the switch and you get a little spark. Jumps across the gap. Little lightning bolt. And he believed, what he then did is he set up a receiver. And the receiver was literally the same object with the same gap. So this gap here and this gap here have the same width. And what would happen is that he would set up his original transmitter, get the spark, and then over several meters away he would have his receiver, and as long as these two things what would happen is that suddenly he would get a current reading. Which would mean that what has happened is a wave of energy has crossed this sort of several meters of distance between the between the transmitter and the receiver. And because it sort of matched that little gap there, it's been able to transmit some of its energy into the wires and generate a current signal. And this was the first sort of evidence of what became known as radio waves, but also, and another type called microwaves. The radio waves just being smaller versions of the microwave being just smaller gaps. So radio waves can be really big. They can be sort of like a kilometre or so in their wavelength. Microwaves tend to be very small, a few centimetres. And when Hertz was first doing it, what he was really doing was generating what we would now probably call microwaves. But with his experiments, he made his gaps bigger. He designed different ways of generating these waves, send them out over longer distances, and find this ability to send a signal from one place to another place. And this obviously changed the world, because now so much of our communication, our wireless communication, relies on this. We don't generate them by making sparks anymore. We have different ways of making these waves. Here's just a very crude way of making them in the 1800s. But what we do have is this ability to generate these wireless signals and send them all over the home. So your wireless broadband, various speaker systems that talk to each other, all these things that occur without having wires in them originated from this single discovery. But even sort of what was quite hilarious was that even with this this experiment and this being proven, Hertz himself had absolutely no clue that this could have any impact at all. In fact, he went on record as saying that they were largely useless. In terms of his, when he stated the possible use of his radio wave experiments, he said the following: "It is of no use whatsoever. It just is an experiment that proves Maestro Maxwell was right. We have these mysterious electromagnetic waves that we cannot see with the naked eye, but they are there." When asked about the applications of his discoveries, Hertz replied, "Nothing, I guess." It was a very, very, lack of foresight in what this could mean if you could send signals from one place to another without having to actually have a wire. And so that became known via many early radio signals and things became known as the wireless, this magic of wireless technology, which is still permeating our entire system today, from mobile phones to radios to televisions to satellite communication, all of it happening in terms of radio and microwave communication. And yes, even the microwave that you use to heat things up. So what went in here was radio waves and then microwaves. And that, really, anything that's longer, anything that's sort of bigger than that, if you carry on going that way sort of forever, we just keep calling them radio waves. We haven't determined that there's another. Things are going to come thick and fast for the last two. The next one would be discovered in sort of November. I don't know why I've sort of given you November 1895. So only less than a decade after the discovery of sort of radio and microwaves by a person called Wilhelm Röntgen. It's got the umlaut there. Now, Röntgen was studying this largely by accident, and rather than me continue to do this, there's a little video link to talk about X-rays. So what I want you to do is to pause and watch the X-ray video, because that will give you a little bit of a different sort of flavour for the discovery of these rays, and sort of be able to visualise what we call a cathode ray tube. So having done that, this was the discovery of the X-ray. Originally, where did the term X-ray come from? X was just used by Röntgen as a kind of a placeholder for unknown type of radiation. And the name stuck because it was kind of mysterious and cool, and because of all the big sort of the plethora of things that got on board with this idea of X-rays. Röntgen didn't like the term X-rays, but that's what we got. And so we ended up with these things called X-rays. And that would be the electromagnetic spectrum would be completed and filled out in May of 1896 with the discovery of radioactivity by Henri Becquerel. Although it would take a few more years for it to be definitively shown that there was a bit of it that was related to the electromagnetic spectrum. Henri Becquerel was basically fortunate. Building on the work of Röntgen, a lot of people started bringing photographic film into their labs to see if they could also discover anything that might darken photographic film, to do experiments with these weird X-rays that everyone was talking about. And Henri Becquerel was investigating, uranium. Now, uranium, certain salts of it are warm to the touch. They can give off phosphorescence. They can make various things glow. So he was trying to work out this sort of, what the properties of these weird rocks were. And at a certain point, what he had is he had the uranium block resting I think possibly due to chance, on a sort of sheet, which inside of which was a photographic film. So it was a sort of something that was encased within an envelope. It was kind of meant to be put away and secure. And what he discovered, much like Röntgen's emanations from the cathode rays, is that the uranium that was sitting on top of this caused the photographic film to darken. And he ended up with a picture that looks a lot like a picture that you get from an X-ray of a film that is just dark where the uranium has been resting on it. So something was coming out from the uranium and causing it to darken. Oop, that was not what I wanted. I wanted the thing to darken it. And this shadow that he had, he realised that it was a very similar property, a very similar phenomenon that was going on. Now, he was able to discount the fact that it wasn't the same as the X-rays because he didn't have cathode ray tubes in his lab. He was able to work out what it could and couldn't be. But he was able to identify that they were the same thing. Now, originally he tried to call them Becker rays, a little bit. But over time there was work done over the next few years by people that you might have heard of, Marie Curie and Pierre Curie, in finding more examples of things that had this impact. And then finally, a gentleman who was working at the University of Manchester called Ernest Rutherford, who was able to categorise that there were slightly different types of things, that radioactivity that could do this. It could come from, say, a rock sample. And two of them are called alpha and beta, which we'll meet in. But the third type was a wave of energy, and that became known as gamma rays or gamma radiation. And this became the final part of the puzzle. This is what we call the electromagnetic spectrum, the full spectrum. The differentiation of different things is sometimes a little bit vague, in the same way that sometimes not entirely clear when you go from blue to indigo. Exactly when you go from radio to microwave isn't always clear. It isn't always a specific, there's no specific line. So we tend to differentiate them in terms of what we kind of use them for and what we do with them. And this is the EM spectrum as it is, running in order: radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays. And in terms of going across them, as we move from this direction upwards, in terms of the properties of the waves, what they are as we go upwards is increasing frequency as we go along this line. As all of these types of electromagnetic waves are part of a much broader spectrum than the little bit that you get to see, that means they have certain things that are in common. Okay, so what they are, all electromagnetic waves are all transverse waves. Yeah, they are all transverse waves. They can all travel through a vacuum. And they all travel at the speed of light. In a vacuum. Which, if you ever need to use it, you'd be given it. But for reference, that is 3 times 10 to the 8 meters per second, or that is 300 million meters per second. It's where the it's where the sort of like the big numbers can sometimes turn up. Okay, how do they then differ as you go along the EM spectrum? So as you go along the EM spectrum, the frequency increases from radio, as you move from radio to gamma, but also the wavelength decreases from radio to gamma. Okay, but what happens is, because they all travel at the same speed, as one goes up, the other goes down. So frequency is getting bigger as you go from radio to gamma. Wavelength is getting smaller as you go from radio to gamma. And it's this sort of change here, these two changes, is what ultimately determines how we interpret them. It's what means that an ultraviolet ray and a wave of ultraviolet radiation will be invisible to your eye, but will give you a suntan. Whereas infrared will be invisible to your eye, but will make you feel warm. Whereas radio waves, you barely notice them at all. They just sort of travel largely just sort of through you. So you don't tend to worry about them.